Now that we know the volume of 1 mole of gas, it's possible to get into and out of BCA tables by using either the molar volume of a gas or the ideal gas law. Much like last chapter, we used the molar mass to get into and out of units of moles and thus get into and out of the BCA table. So now we can start a problem with grams of a solid or liquid or with liters of a gas, and in either way get into the BCA table and back out of the BCA table again. It's going to be more important than ever to pay attention to what you're given when you start and what the problem's asking for. So this says, what volume of hydrogen gas? So that's what we're looking for. So I'm going to circle this here. Volume of hydrogen gas is what we're trying to end up with. Will be produced if 25 grams of calcium hydride react with excess water according to the following equation. And so you've already been, in this case, given the balanced chemical equation. We know 25 grams of calcium hydride. That's the amount we're given. And we want to know the volume of hydrogen gas. So much like we did with BCA tables, since we have units of grams, the very first thing we need to do is get into units of moles. And grams is related to moles using the molar mass. So I'm going to come off to the side, 25 grams of calcium hydride, CaH2. We need to figure out the relationship between grams and moles is molar mass, so the grams in 1 mole. Now I'm going to go to my periodic table and look up calcium and hydrogen and add them all together. And I found that that was 42.094 grams in every 1 mole of calcium hydride. So doing that math, I find that 25 grams of calcium hydride is equal to 0.5939 moles. So I'm going to put that into the BCA table much like we did before. We are starting with 0.5939 moles of calcium hydride, and it does say in the problem there's excess water. We usually do not start with any of the product. We're going to use up all of the calcium hydride according to our 1 to 2 mole ratio. We need twice as much water. So twice as much water, we would use 1.1878 moles of water. And we form, there's a 1 to 1 mole ratio of calcium hydride and calcium hydroxide. So for every 0.5939 moles of calcium hydride that are used, we form 0.5939 moles of calcium hydroxide. And there's a 2 to 1 ratio between calcium hydride and hydrogen. So we'll form 1.1878 moles of hydrogen. And we'll just complete the BCA table. There are no calcium hydride left at the end. It's all been used up. There will be excess or leftover water. We've formed 0.5939 moles of calcium hydroxide, and we have formed 1.1878 moles of hydrogen. So now to figure out where to go next, I refer back to the problem. The problem says we're looking for volume of hydrogen gas. What we know right now is moles of hydrogen gas. And so we can get from moles to volume by several different ways. First, if you're at STP, you could use the molar volume we discovered in the lab, 22.4 liters in every 1 mole. However, in this particular problem, that is not going to be helpful because this specifies that the temperature is 30 degrees Celsius. That's not standard temperature. And the pressure is 0.79 atmospheres, which is not standard pressure. So the easier method, 22.4 liters in every 1 mole, isn't going to help us here. Our other option would be to use either a PVTN table or the ideal gas law. Probably the easier of the two is going to be the ideal gas law. That is it's a little bit trickier, a little bit more math than using the molar volume at STP. However, it is more broadly applicable at other temperatures and other pressures. So that's going to be our choice. I'm going to flip to the next slide because there's a little bit more room there to do this work. And I'm taking this 1.1878 moles of hydrogen and carrying that forward. If you want to use the PTVN table because you've got those calculations down and you don't want to worry about it, you're going to compare things to STP every time. So STP is 1 atmosphere and 273 Kelvin. The volume for STP is 22.4 liters, and the number of moles for STP would be 1 mole. And we would compare to that 1.1878 moles. We want to know what the volume is. The temperature, it said, was 30 degrees Celsius, which is 303 Kelvin, and the pressure was 0.79 atmosphere. And so you would make a comparison and do your calculation based on that. So if pressure went down, the effect that would have on volume would be to cause volume to go up. So our first step in our calculation, 22.4 liters, times we need a volume going up fraction out of pressure, which would be 1 over 0.79. The effect of temperature is next. Temperature went up. That would affect volume and cause volume to go up. So we need a going up fraction, 303 Kelvin over 273 Kelvin. And finally, the number of particles went up, and that would cause volume also to go up. So for our number of particles, we will have 1.1878 moles on the top and 1 mole on the bottom. And you would simply multiply that out. And I found that that would be 37.38 liters, or with two significant figures, just 37 liters of hydrogen. So that's one way to solve the problem. The second way is to use the ideal gas law and just plug in the things that you know and do more of a solving of formulas. The ideal gas law is PV equals nRT. Use the pressure from our problem, 0.79 atmospheres. The volume in the problem is what we're trying to solve for. We know the number of particles is 1.1878 moles. R, and remember there are several different values of R. You want to pick the one that matches with units of atmospheres and moles and Kelvin, which is in this case 0.0821. And the temperature is 30 degrees Celsius or 303 Kelvin. So we plugged everything in. We're going to solve for volume by dividing both sides of this by 0.79. And volume equals, again, 37 liters of hydrogen. So you can pick whichever method makes more sense to you, either comparing back to STP using a PTVN table, or you can use the ideal gas law. To summarize, we now have two different ways to get into and out of BCA tables. If we start with moles, we'll skip step 1 completely because you can go right into the BCA table. But if we are given units of grams, then we'll use the molar mass to convert grams into moles before we use the BCA table. If we are instead given volume of a gas, we now have a couple of ways to convert volume of a gas into units of moles. So trying to convert liters of a gas to moles, we could use 22.4 liters for every 1 mole of gas. That works for STP and only STP. Or we could use the ideal gas law, and that works for every temperature. So then we use the BCA tables just like you're used to using them last chapter. You use the coefficients as mole ratios to relate moles of one chemical to moles of another chemical. After you've used the BCA table, you might want to enter in units of moles, in which case you're done. However, if the problem asks for the measurement in units of grams, then you need to use the molar mass to convert moles back into grams again. Or the problem might ask for the volume of a gas, in which case you're going to use either the molar volume, 22.4 liters for every 1 mole, which works at STP, or for any temperature and pressure conditions, you can use the ideal gas law to relate moles of a gas to volume of a gas. We will learn at least one more way to get into and out of a BCA table, but at this point we have 3. Starter in with grams when we use molar mass, starter in with moles where you can go right into or out of the BCA table, or start or end with the volume of a gas, in which case you can use the ideal gas law or the molar volume of a gas.